So we are the Kingetics team. I'm Mark Gronowski.
I'm Jan Oakman.
Paul Carroll.
I'm Alice Wakeman.
Alright, so according to National Institute of Health, it's estimated that 2 million Americans live with amputated lower limbs, and this is due to cancer, diabetes, heart conditions, and trauma. These numbers are even more ridiculous in third world countries and war-torn countries, as these are caused by limited health resources, political and economic factors. It's estimated that a basic prosthetic costs $3,000 to $7,000, and these numbers are ridiculous considering its use. Last year alone, it was estimated that 20,000 Ukrainians underwent amputations, and it left over 50% of them without prosthetics. So the motivation of this project would be to design and build an easily assemblable, cheap prosthetic. This prosthetic will be distributed to war-torn countries such as Ukraine, third world countries, and will be able to help tens of thousands of people to access these prosthetics and be able to live semi-normal lives. Since our prosthetic is meant to be easily assemblable, we're trying to use easy tools such as hammers or jigsaws, and should be able to be assembled by a person with minimal technical knowledge. So, as mentioned before, our responsibility team worked with NDSU in previous years to develop a testing apparatus that was able to test if our design is feasible. And so during the spring semester, we're going to be collaborating with them around January, February to make sure that our design works, and also publish our testing in our internet journal. So the diagram shows the region where we estimate our prosthetics to be used, and we are not responsible for developing the sleeve or the connectors to the prosthetic. We'll simply be shipping our design that will show the next slides. So the main objective will be to have a prototype so we can be able to test it with the testing apparatus that we see. We'll be performing FDA analysis as well. We'll also be making sure that our design is likely to shipping this to other countries. We want the shipping cost to be as minimal as possible to maintain our goal of $100 a piece, and especially before we be publishing this.
To give you guys a little bit more background about the gate cycle that we talked about a little bit more later. There's 5 different parts, starting with the heel strike. As you can see in the first picture, those are the 5 different parts. It starts with heel strike, flat foot, to midfoot, to heel off, to toe off. And with that initial heel strike, you're trying to absorb that initial shock by using the mechanical materials, elastic properties, to use those materials, elastic properties, so we can create an effective way to store that mechanical energy at the input and then recover that later throughout the gait cycle, allowing a person to walk easier. So current state of the art with prosthetics, these first 2, Bashford and Hosser, these are very high-end prosthetics, and some of these high-end prosthetics can end up costing up to even $55,000, which again is very, very expensive for especially some war-torn countries and even third world countries. So a lot of these high-end prosthetics use an ankle joints as well. That is something that we are not adding to our prosthetic because of our dual lever system that will be explained a little bit later. That allows that initial impact with the heel strike and bends our material to create more of an easier walking motion, and that's going to replace the ankle. Project Circle G is a company that's kind of similar to us trying to use recycled plastics to make a cheaper prosthetic. So this is our current block diagram. We've created a SolidWorks design that you'll see here shortly. We recently finished our FEA analysis, and next semester, after we create our full prosthetic, that involves a pylon connector, different connection points with bolts, our foot, and then our dual leaf spring. We use our robotic testing up in NDSU that they have a full testing apparatus that they've already created a couple years ago. So this is the Kingetics insole that was previously created by Dr. King and the team up at NDSU. The black part up there that's on the diagram is the foot cradle that Paul currently has in his hand right there. Our prosthetic is going to replace that component of the foot. That bottom plate that is in green, sorry, but in green is going to be placed into a bottom of a shoe. So we have that, and Paul is holding that right there. That will be placed into a bottom of a shoe and be held separate from our prosthetic. So this is a video of how our prosthetic, or how the insole works. That top part is the cradle again. As previously said, that was going to be replaced by our prosthetic. But you can see that initial heel strike, we're going to try and store that mechanical energy, and it should be transferred throughout the loading response, through the pronated ankle up to the supinated midfoot of the stance. And then as you go to toe off, all that mechanical energy should be used throughout the gait cycle, allowing you to be able to walk easier and reduce impact on joints through the kind of the elastic properties of the initial heel strike.
Okay, so here's our current design solution. We are using aluminum 6061 to build our prosthetic. We have a 1-inch diameter pylon, which is sort of the standard size for most prosthetics, with a 8-inch thick wall. We are using bolt connections at each of those bolts to be able to assemble our prosthetic, keeping it easy to assemble for anyone without technical knowledge. The flaps on the sides are to help fill out the shoe and be able to tie it down with the prosthetic inside. Here is a picture of our prosthetic with the Delrin acetoplastic underneath and shown inside of the shoe.
So this is a bolts calculation. We use a factor of safety of 9 and multiply this by a load of 215-pound human, and found the design overload to be 2,250 pounds. And so we calculated this by dividing the grip strength of an aluminum screw and found the area to be 0.264. We rounded that up to 0.318 and found that diameter needs to be a 1/4-inch, 20 threads per inch for a course and for a screw, and a 1/4-inch, 28 threads per inch for a 5 screw.
Okay, here's the first of our finite element analysis simulations. This shows the stress on the prosthetic during the heel strike, with all of the forces acting on the heel at a 45-degree angle. You can see that none of the stress gets to anywhere close to the yield strength of the material, so that's a good thing. And this shows our factor of safety with that, reaching at its lowest about 1.5 to 2. Here is the prosthetic during the midfoot with all of the forces acting straight downward during running. And for running, the forces are about 2.5 times what they would be during walking. So this is a pretty high force. We use a average human of about 900 pounds, and so this is about 2,200 pounds of force on this one, or newtons, sorry. And so here's the factor of safety of that at around 3. And here is the toe off, where all of the forces are acting at the toe. And as you can see, this one is not much of a concern for us, with pretty much everything being used.
So when we were trying to decide what material to use, one of our constraints would be had to use aluminum because it's light and it's relatively cheap. So research into different alloys of aluminum, and we did on using 6061 P6, which has a yield strength of about 275 megapascals, which, if you pay close attention there, you can see none of our simulations wrote 150 megapascals. So this material should have very little issue with like the max force that we apply to it. On top of that, the other worry, especially with looking at prosthetic, is that it's going to wear down over time. It's going to have some fatigue, and aluminum is very well known to have fatigue. So because of that, we did some research and we found, and we wanted to use about 8 years because this is something that's not going to be able to be replaced very easily, but we do want individual components to be swapped if necessary. So given that you're taking about 4,000 steps a day, which is the average, and walking applies about 30 megapascals, you should be able to make this thing last around 8 years. So this is a Gantt chart. This is what our plans are upcoming as well as been in the past. So next week is when we present this to our senior design committee for what should supposedly be our sort of final design going forward with the all the nuts and bolts and get everything approved from some professors here. And then in the next semester, we're planning to assemble it and then take it up to NDSU in order to run some tests, get some numbers, compare to what our FDA analysis is, and get a more accurate picture and see if anything else needs to be changed. So our estimated budget, as mentioned before, we want to say under $100, and as you can see here, our current estimated cost per unit is around 65. This includes a pylon, a square foot of aluminum, which will be cut and molded into the various components for our prosthetic, as well as a sheet of Delrin, which is a type of plastic which is being used at the spring plate. And then just an estimated cost of around $10 for various bolts and connectors. Does anyone have any questions?
So for what it's worth, a prosthetic is a medical device. So FDA regulates them. And yeah, Todd's looking at me like, yeah. I just quickly looked at FDA and it's called Class 1, which means you don't need to notify them and get a release to market it, which is good. But that's probably not true internationally, because then there's another set of standards. But all I'm suggesting is that have somebody take a look at it. Call me if you need some help, and make sure that you're talking about it in your design reviews. You know, because it is a requirement, and all the stuff that you're doing, it would probably end up being submitted to one of the regulatory boards as it happens. And I don't know where you are with planning to manufacture the thing. You know, I mean, I think being able to manufacture it for $65 is probably a pipe dream, but I understand your point in trying to do that. But then all these regulatory issues come into play. You know, the manufacturing sites have to be ISO certified, et cetera, et cetera, et cetera. So I just want you to know about that and keep that in mind. It is a medical device. So there are rules and requirements that apply.
We'll take you up on that. We'll take you up on that help.
Yeah, sure. You know how to find me.
I do.
So you got your like fatigue values from like number of steps of 4,000 steps.
Yes.
Is that, where'd you get that average? Is that for like US or is that for like a target of like maybe a third world country?
That's US, average 4,000 steps a day. We figured also that if you're using a prosthetic, you're probably going to be walking a bit less, just due to the nature of the whole thing you have going on there. So we figured 4,000 probably a good estimate.
Okay. And then also you had on your bolt calcs, you had I think it was 250 pounds load, and then on your FEA you had up to like, I think it was 900.
Yes.
Is that for a different, like, what bolts are you, does that force not go through the same spot, or I was just curious about that?
The 250 pound is roughly similar to 100 kilogram of person. So 900 newtons for the.
Well, yeah, you talked about like it was higher load, like when you're running versus the static force.
Yeah. That's why we have such a high factor of safety for bolt complex.
Gotcha.
You mentioned there was a factor of safety of 1.5 in this area.
Yeah, for this one, as you can see, that gets into the red a little bit there, so that's something we'll have to look at.
How does the weight of this prosthetic compare to like what it's replacing for like a person's like actual?
So, a normal person's like, maybe you kind of just cut off the leg right there, it's usually around like 5 to 7 pounds. And our prosthetic, in our recent calculations, I don't know if it changed, we just kind of changed our material, but it's right around 1 pound.
Other prosthetics, roughly what the traditional prosthetic thing.
It's usually in that 1 to 5 pound range, depending on what kind of materials they're using as well.
You know, one other quick one. One of your senior design predecessors developed a whole set of sensors in shoes. You guys might take a look at what they did, because there might be some technology or something there that might help you with your work. He knows that project. That's 3 years ago, maybe 2 years ago.
I
Anyway,
think they graduated in 2020 when everybody went out of the pandemic.
they were runners trying to improve their running game. So
You mentioned, did you say you were using aluminum quarter 28 volts? Or are you,
No, regular grade 5.
are you worried at all with the 2 point, or the 2 points of contact there that the bolts are just gonna waller out the prosthetic, the aluminum prosthetic?
A little bit, yes. We've looked into using steel brackets, those in place.
Is weight reduction like always a goal for prosthetics, or is it more, is like they're an optimal weight, or is it always make it as light as possible?
Well, the goal is to kind of try and make it similar to how the leg was previously, so it doesn't feel kind of awkward when you're going through those gait cycles. But for our purpose, we're kind of sending it over to third world countries and kind of shipping costs and stuff like that. That's why Dr. King wanted us to try and keep it at a minimum weight, so the shipping costs would kind of be sure to us.
Any other questions for this team? All right, good job.